Okay, so some business announcements. So some business announcements. So I've been trying to think about what to do with the rest of the semester. We're quite a bit behind where we were last year, and I'm happy with that. I think we went a speed I liked, but it's sort of thrown off sort of my plans. And that combines also, I have some travel that I have to do that came up in the last week of the semester. So here's what I propose to do, and I hope you guys are okay with this. Basically what happens is that the work that we've done so far on the hydrogen atom and the work we're about to do on statistical mechanics were the final things that are normally on the third exam. And then after that, we sort of go into other topics, which this year is going to get squeezed a bit, and that also are more just sort of qualitative, and in the past I've only put a little bit on the final about them. What I propose to do is then delay the third exam till essentially the end of the class, okay? And so therefore what you're really going to get is BAM, that exam, which is on the work we just did and the work we're just about to do on StatMech. Then we're going to stop and kind of have fun for about a week on particle physics and cosmology. I'll try to I might ask you a question or so just, to make sure you were there or, conscious at the time. But more or less that will be it. And so then that third exam will simply be directly translated over into the final, because the final is going to be just all the material that were in the first three exams. And so that will probably be on the Wednesday before the last day of class. And then given my travel, I may just cancel the last day of class. So that's probably what we're going to do. Is that okay with everybody? Yes. Yeah, I kind of thought you actually might like that. I wasn't sure if you wanted an exam so close to the end, but I think it'll help for studying.
Do we have like a week of, we're the second week of,
Excuse me?
we're the second week of finals, so we have a week of no class before we
Yeah, to be clear, I'm talking about the last week of classes, I think ends on the 5th, right? Oh, I'd forgotten when our exam was. So if our exam's on the 15th, right. But so I'm talking about giving you a third exam on the 3rd. Let me write this down. Okay? And then that'll be the last day of classes. Or possibly, I could even do the exam on the 5th. Okay, but I won't be here on the 3rd. So I thought I'll just give you the exam on the 3rd and we'll take the 5th off. All right? And what it'll mean is that you're going to have a week of we're going to do other stuff that really won't be featured on the exam at any serious level. Okay? So we're going to kind of spread out your homework load, if you will. Well, the homework I'll do ahead of time, spread out the work. Okay. Oh, can you see this cup? You can't read that. It's got a little picture of sort of like a guy with one big bright eye. It says sleep is for the weak. Probably not a healthy motto. All right. Okay, so we're going to talk about statistical mechanics. And a comment on what we're going to do. The book, I'm not going to try to cover everything that's in the chapter in the book. We're going to pick our way through a little bit, partly because we went so thoroughly through quantum mechanics, there's just not time. And partly because I don't feel that it's that appropriate. But I'm going to go into a few topics in some detail just to give you a taste of this, okay? And so I owe you a few things. I owe you this midterm grade, apologies. But I'll send you that, and I'm also going to send you some comments on which parts of the chapter you're responsible for. Okay? So, a basic idea in statistical mechanics, as I said early in the year, is that if you have a huge number of particles, suppose in a gas, in a liter of gas, where you have essentially nearly Avogadro's number of particles, 10 to the 23rd, clearly you can't, in any practical way, derive equations for how all those particles move. But just as clearly, from chemistry and from the developments that happened up till mid-19th century, there is a lot that must be simple, though, right? So you have the ideal gas law and the various subversions of it, Henry's law and whatnot. Not Henry, Charles's law and Boyle's law and things like that. That told you how pressure and temperature and density were related, right? So there is some underlying mathematics to it, even if clearly you're not going to sit here and write down 10 to the 23rd equations and start deriving, all right? And these were developed in the form of statistical mechanics. Just a bit of terminology. We're going to distinguish between microscopic particles, microscopic properties. So here would be the velocities of atoms, or the energies of individual atoms, okay? And macroscopic properties, right? The general English word macroscopic meaning sort of large, okay? So this is going to be things like, well, what we encountered in the ideal gas law: pressure, total energy, temperature, etc. Oh, well, another biggie is heat capacity, right? Which is the change in energy divided by the change in temperature. And then there's others, although those are the first things that spring to mind when we think about thermodynamics. And so, sort of historically, and I mean this makes a lot of sense, things like the ideal gas law developed, and then thermodynamics. I think I mentioned this in the first lecture. The very fact that that when energy flows from one system to another, that there really is strict conservation of energy. I think I mentioned in the first lecture that that wasn't sort of obvious. I mean, now that we have modern physics and you learned energy conservation probably very early, if not for last year, then in high school, you say, oh, well, it's obvious if heat's going to flow, energy is conserved. It really wasn't obvious. I mean, think of any practical system. We lit a fire last night in my fireplace, right? I mean, the notion that on a microscopic, exact, quantitative basis, there's some accounting for energy where I think about the sunlight that hit the plant, that hit the tree, that grew the tree, and then then it cooled down because it was a cold night, and I carried it in and I stuck it in the fire and I lit the fire, and all of that stuff happened, and all through all of those processes, only some of which were heat transfer, but it was a whole set of chemical processes and a lot of heat transfer that in fact, all the energy was conserved. I mean, that was sort of an achievement to realize that and to prove it, right? I mean, you have to actually have a little bit of you have to very well thermally isolate a system to show that like energy, just simple energy transfer between a hot thing and a cold thing truly conserves energy. Like if you heat something up and you measure the heat you put in terms of pure energy, watts, and then to show that, if it transfers to another thing, that it all works out. All of that is just by way of saying that, so we think of these microscopic properties and these macroscopic properties. Thermodynamics was the development of talking about all of these macroscopic properties even beyond the ideal gas law. There's a whole, it's a sort of a rich field, thermodynamics, and the concept of entropy, which I'm going to introduce today from a microscopic viewpoint, but it was developed from a macroscopic viewpoint. Again, as I mentioned in the first lecture, there was no deep understanding, but people introduced it. Well, I shouldn't say there wasn't a deep understanding. There wasn't a microscopic understanding, but people introduced the idea of entropy as the ratio of a change in heat, a heat flow in a given situation. The heat flow divided by temperature turned out to be a useful quantity, and they could calculate with it. And that they identified as entropy. And Carnot is the person most associated with recognizing that you could figure all about the maximum efficiency of engines and whatnot, because they were developing steam engines. Okay? In fact, it was steam engines that really pushed this whole thing along. And you can imagine why it would. These were real engineers. Carnot, it's actually very, very deep stuff that he was dealing with, entropy and the second law of thermodynamics. But he was an engineer. He simply wanted to know how engines worked. And you can imagine why, right? Because when you started to really harness a steam engine, you know, you can see what it did. It was, you know, a large part of the Industrial Revolution was figuring that out. And it's clearly very, very important to people. But there was no microscopic understanding. Okay, so let's start to develop a microscopic understanding. And the simplest example, and I kind of talked about it with you the first day, is just to take a box with some particles in it. You know, we can think of this as, you know, atoms in a gas. Okay? And to ask questions about, well, where are those particles going to be? You know, the question you would ask is, or how do the particles distribute themselves? Okay? So it turns out there's a nice way to approach this. Let's start with an example of 5 particles in 5 boxes. If you will, you can think of this as 5 students and 5 chairs. Okay, so just take 5 of you. Don't go to some other chair and start sitting down. So 1, 2, 3, 4, 5. The first thing that happens is one person or one particle sits in one box. Okay? And okay, one person could have done that, or one of the other people could have done that. So there's 5 ways that a particle could go in there. Or in fact, I'll quit calling them particles. So it's 5 students. You know, 5 of you, right? And so one student sits here, and we talk about all possible ways. Any one of 5 of you could have sat there. That leaves 4 people left over. Any one of 4 people could have sat there. That leaves 3 people left over. So any one of 3 people could sit there. Now there's 2 people left over. One of them sits there, and there's only one person left. And there's only one way they can sit. And if you think a second, that really, 5 times 4 times 3 times 2 times 1, that is the total number of ways you can sit. Right? That will cover all possible combinations. Whoever ended up sitting here, they got counted for one time sitting there, because you first let all 5 of them sit there. But you just said once you picked them, there were 4 left, etc. And this mathematical thing is called 5 factorial, right? N factorial means n times n minus 1 times n minus 2, dot, 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 down to 1. And there's the special definition that 0, no, well, let me just leave it at that. I think 0 factorial is 1. Fine. Now, what if these are quantum particles? Remember, quantum particles are different than normal particles. If you guys are all quantum mechanical students, you're all going to get the same grade. You all sleep in each other's dorm rooms all at the same time, and no one can tell which dorm room is which. All sorts of weird stuff, right? Because you're truly indistinguishable. So these were distinguishable particles. Sorry, and I didn't label what this was. This was the number of configurations of the system. All right. If they're quantum particles, there's only one configuration. I put all 5 particles in, all right? And there's only one way to do that. Okay? Okay. Because if I switch 2 particles in quantum mechanics, I haven't done anything. If I really want to talk about it, I'll label the particles, but then I'll write the 5 wave functions down, and then I'll add it where I swap 2, and then I'll add it where I swap 2. And it's just an expanded version of what we did with 2 particles. And then the wave function will literally not change if I swap 2 particles. And so therefore they're indistinguishable. And that's the way nature behaves. We didn't just play mathematical games, that's the way it is. All right. So fine, that's sort of warm up. Now let's consider a box with 2 halves. And what we're headed towards here is a statement I made in the first lecture that if I ask the question, randomly, will all the air in this room end up on that side? The answer is no. Well, okay, so let's approach it mathematically. I have the same 5 particles, and so I could put all 5 particles over here, say. All right? If they were distinguishable particles, I would have 5 factorial combinations. That's 5 times 4 is 20, times 6 is 120. There's 120 ways the particles could rearrange themselves. But they're not distinguishable. There's only one way. Okay? And in fact, if you will, well, okay, so there's only one way. So having 5 and 0, there's one way. All right, well, what about 4 and 1? What do I do there? Okay. There's a special type of logic. How many of you have seen this before? Only a couple. Okay, good. I thought maybe a bunch of you would. There's a special sort of logic to this. Let me try to make it clear. First, I say that effectively there were 5 slots. There were 4 slots over here and a slot over there. So there's 5 factorial total combinations. And this is considering them to be distinguishable. Okay? And I'm going to account for in a second for the fact that they're indistinguishable. There's 5 factorial total ways to move these around because I'm basically saying, yeah, one's over here. And even in quantum mechanics, I'm going to distinguish the right side of the box from the left side of the box. But initially, I think that on the left side of the box, I can distinguish all 4. The fact that this is over here and those are over there isn't really going to change the fact that there were 5 particles in 5 places, 5 factorial total number of ways. Now, though, on the left, there were 4 factorial equivalent configurations. On the right, there's 1 configuration. All right? So I thought I had 5 factorial ways to do this, 120. But on the left, if they're quantum particles and they're indistinguishable, I put 4 in there. And the reality is I can't distinguish them. So even if I think of it as being 4, like, okay, you know, the room has 5 seats on the left, 5 seats on the right, and I've got 4 students there, and there's 1 student there. If the 4 students on this side can't be distinguished where they're sitting, then that's 4 factorial. 4 times 3 times 2 is 24. 24 states fewer than you thought, okay? But it turns out the answer for 4 and 1 is not, you might think, oh, well, okay, so there were 120 minus 24 configurations. That's not the right way to look at it. It's not that. If you had the 120 configurations, and suppose I swapped 2 students and it mattered, or sorry, if I swapped 2 students and that didn't matter, just the 2 students, clearly I'm cutting in half the number of really distinct things. In other words, suppose I said, I have you 5 students, and I put you in one place, and there's the 5 factorial combinations, 120. But then I just say 2 of you are quantum mechanical, and I can't distinguish you. All right? And so that means for all those other configurations, if I swap 2 students, that's the same. I'm clearly dividing the total number of configurations by 2. Do you see that? So the right way to think about this is that the number of configurations, I'll write it as C, is 5 factorial divided by 4 factorial. Okay? I divide by it. That's how many configurations on the left were the same. And in fact, there was also 1 factorial over on the right. And the way I got 1 is that there were 5 students, 4 of them sat on the left, that left 1 on the right. Okay, so this is the total number of configurations. This is the left, it's the number of redundant, if you will, configurations. And that's on the right, the number of redundant configurations. And that's the total number of configurations if I have 5 total and 4 go on the left, and what's implied is therefore 1 left over was going on the right. This is sometimes written as 5 over 4 in brackets. That's the notation the book uses. Does that seem, you follow that? This isn't fundamentally important, but it comes up on occasion, and you know, and it's a little bit, maybe it's a little bit unusual thinking compared to what you might have seen before, but it's straightforward. A little bit unusual. And that was easy enough to compute. So for instance, the 3-2 case, 3 particles and 2, 5, 3 is 5 factorial. Oh, sorry, I didn't compute this. 5 factorial over 4 factorial. Let's write it again. Of course, and at times 1 factorial. Of course, actually, I don't want to multiply this out. I want to just recognize that's 5 times 4 times 3 times 2 times 1 over 4 times 3 times 2 times 1. That's 5. All right, so this is 5 factorial over 3 factorial times 5 minus 3 factorial. It's 5 factorial over 3 factorial, 2 factorial. So 5 times 4 is 3 times 2 times 1 over 3 times 2 times 1 over 2 times 2 times 1. So those things wipe out these. That's a 2. That's equal to 10, right? Fair enough. And the general formula for n little n is n factorial over little n factorial over n minus n factorial. Okay? So this is basically if I have n things and I'm choosing, I get two choices for where to put them or how to, it could be a box with particles side to side. It could be particles that are going to go into one energy state or another energy state. It could be particles that I'm going to paint blue and particles that I'm going to paint red. It doesn't much matter. It's a two-state system with n particles, and you're choosing little n to be in one state and the remainder in the other state. This is called the binomial coefficient. Do any of you know why? It's called the binomial coefficient. No? No one? It's because if you have x plus y, just a mathematical thing, algebra to the n, to capital N, right? So I could have x plus y squared, but like, what if it's to the 40th or something like that? This is x to the n. You know that. There's going to be one term like that. And there's going to be one term y to the n, right? And there's going to be a term, that there's going to be a term x to the n minus 1, y to the n. And it's going to have some coefficient. And if I asked you to find it and it was n is 40, what would you do? You'd go on Wikipedia probably or something, or you'd pull out some book. But if you remember, in fact, if you've ever seen it, this in fact is, this is that. Okay? So the coefficients of the terms in this is just a binomial, two terms to the n power are that, okay? Yeah?
Isn't there only one term with y to the n? Should that be y to the n?
This is a 1 there. I didn't write the thing in front, yeah.
No, that is the second, the first exponent of y.
X to the n minus 1.
Oh, that's a 1. Sorry, thank you. Thank you, sorry. Yeah. Is that what you were laughing at? No? Huh? Okay. Fine. Okay, so why do we do all this? Well, if you start to plot, and let me erase this. And this is in your book. This is right at the beginning of your book. Your book skipped the derivation of, well, the talking I did to sort of explain where this comes from. But it does do this following set of plots. It's quite simple. If we plotted well, let's make a graph of these numbers, okay? We have, if I have 5 and 0, that was 1, because it's 5 factorial over 5 factorial. If I have 5, 1, that was equal to 5. 5, 2 was equal to 10, was equal to 5, 3, right? Clearly, because that's, if I choose 2, I'll have 3 left over on the other side. This is the inverse of that. This is also the same as 5, 4. Okay? And this is also the same as 5, 5. So if I make a graph of little n for capital N equals 5, at 0 and 5, 1, 2, 3, 4, okay, I had let's put it about there. 1. Let's put it about there. 5. Then it's going to be about there. So I have 1, 5, 10, 10, 5, 1. Okay, simple graph. All right. If I take n to be a bigger number, the book graphs 40. Okay? Oh, and the peak here is, that's 2, that's 3. It's straddling 2.5, which is half of n. So this point is n over 2. If I pick n equals 40, I'm going out to 40, and there's a place that there's 20. You get something that looks, and I'm going to draw a curve over the envelope. I really should draw dots, but I'm not going to draw all the dots. It looks something like that. And the peak value here was 10. The peak value here is 10 to the 11th. Okay, for n equals 40. In fact, the factorial, that's coming from the factorial. The factorial is like one of the most strongest functions mathematically, right? I mean, 10 factorial is a huge number. 20 factorial is a really big number, etc. All right? If I change this to 400, these all change. And this thing gets considerably sharper, although not infinitely sharp. The peak value is around 10 to the 19 by changing it by a factor of 10. And then if I take n to be 10 to the 23, which was the example of the air in this room, this thing, well, you can't even, you're not going to plug it into your calculator. I mean, you're not going to take 10 to the 23 and you're not going to test out 10 to the 23, I don't know, and 137 and plot that one. Because if you try plugging 10 to the 23 factorial into your calculator, forget it. But various mathematical, there's mathematical methods for dealing with these very large numbers, and you can go through that, and you basically find that the thing, well, actually, I didn't even do it justice. If I draw the line with the chalk, the width of the line of chalk I drew is too wide. It's an extremely, extremely narrow distribution. It is in principle a distribution. It has a non-zero value over here. In fact, I know exactly what the value is at 0. It was 1. And I know exactly what the value was. Sorry, this is 10 to the 23. And this is 10 to the 23 over 2. It has a value 1 right there. But on any practical graph, those things show up as 0 because this turns out to be 10 to the 3 times 10 to the 23. Okay? So just an absurd number. All right? And that's the reason why all the air isn't randomly on this side of the room compared to that side of the room. I mean, you sort of knew it. But this is a way of talking about it. And it's much more rigorous and mathematical. OK. Let me make a final comment that if I wanted to talk about a probability, let's focus in on this graph. What's the probability of getting a state 1, or the probability of little n equals 2? This value here. There's sort of a type of thinking we do all the time in statistical mechanics, although it's not statistical mechanics, it's simple probabilities. In this system, how would I figure it out? What is it? If you think of a formula, what's the formula for the probability that n equals 2? You don't have to give me a number, but how will I construct the number from the numbers I've got? Exactly. It's 10, which was C of 5 and 2, over all of them, 1 plus 5 plus 10 plus 10 plus 5 plus 1, and all of those, that's C of 5. No, sorry. Wrong terminology. That's the binomial coefficient for 5, 2, etc. All right? Which is 10 over 10, 20, 30, 32, which is 0.3125. Right. So just realize that's what you're going to have to do. Now, in statistical mechanics, a lot of what we're going to do is going to involve setting up systems like this and computing probabilities. And things can change exactly from one system to another, exactly how it works out. But the principles are always the same. If you can write down the total number of states of the system, then that's going to be the denominator. And the probability of any one state is the number of states of the system that have that feature. Okay? So there was 5 configurations or states of the system that had little n equals 2, 2 particles on the left. And then I divide by all the ways the system can be configured. And I bet until we went through this thinking, you weren't going to come up with the fact that there were 32 ways the system could be configured. Right? That you know, realize what we had to do to get to that. Yeah?
Is that just a coincidence that it's 2 to the 5th? That's the total number of states.
Ooh. I don't know. That's a good question. It's not. It's not, because I don't know if this is very deep, but the reason it's not a coincidence was that 1 plus 1 to the 5th, which is 2 to the 5th, is equal 1 to the 5th plus 1 to the 4th times 1 to the 1 times 5, 1 plus 5, 2 times 1 to the 3 times 1 to the 2 plus dot, dot, dot. These are all just 1s. So this is just 5, 0 plus 5, 1 plus 5, 2. So it is 2 to the 5th. Never thought of that. But is that, I don't know if there's anything deeper to that. Amusing. All right. Okay, let me stop there. Okay, so, I mean, most textbooks on StatMech start with this beautiful derivation of particles in the one side or the other side of the box with a binomial coefficient. And you kind of drop the binomial coefficient. We're not really going to return to it after this. But the reason is that it's a really simple, tractable thing that you can wrap your mind around. I hope you followed my derivation of the binomial coefficient. I hope you remember it. I hope it enriches your life. But the point was, it was pretty straightforward to really calculate this number of configurations. So let's go to let's kind of jump again a bit. I said in the first class that Boltzmann, who thought about these things, ended up deciding that, well, entropy had a thermodynamic derivation, and a thermodynamic definition, in fact, it was developed first, that entropy was k natural log of W, or k equals 1.38 times 10 to the minus 3 joules per Kelvin is Boltzmann's constant. S is entropy. And W, and actually I called it omega because that's actually what I'd like to call it, but the book calls it W, so I gave in and I'm calling it W, just like is on Boltzmann's grave. That is the number of states of the system. That's no good. Now, the number of states of the system is something that I can't give you a general formula for. It depends a little bit, one system versus another. However, it was exactly this binomial coefficient for the system we just did, right? The number of configurations, that was it. And Boltzmann said I should take the logarithm of it, and then I should do that. And that's how I should think of entropy. Now, I've got 5 minutes left, and I'm going to show you the definition based on this of temperature. Remember, entropy is a measure of disorder. And let me try to motivate this just a little bit. I mean, W, the number of configurations of the system, does match, right? If I had the two box, the box with the broken in half, if I have all the particles on one side, that was the W equals 1 state, right? In fact, if I take the logarithm of 1, what's the answer? It's 0. Okay, so entropy was 0. If I had the sort of 3-2 or 2-3, that was where the number was 10, and then entropy is maximized. And indeed, there are more ways to wiggle, to configure that. So really, we're just counting the different ways that could be configured, and that's a measure of disorder. And surely, in some vague sense, the 3-2 or the 2-3 states are more disordered than everybody on one side or everybody on the other, right? They're more random. The logarithm, in some hand-wavy way, the reason you want it is because if you don't include it, the numbers just run away from you. Right? Remember I had the one value of 10 to the 23 examined at 1/2 times 10 to the 23. I believe it was 10 to the 3 times 10 to the 23. So some insane number. Why do I keep calling it C? That is sometimes used. But if I'm going to interpret that as W, that's this huge, crazy number. If I take the logarithm of W here, the logarithm of that, well, instead of being, well, okay, this is the natural logarithm, so it's a little more complicated. But if I took the log base 10 of it, instead of 10 to the 23, I'd only get 3 times 10 to the 23, which is a lot more manageable, although still insane, right? But the reason we take the logarithm, just in a very hand-wavy way, is to not have these super enormous numbers, to have better behaved numbers. And remember, when you take the logarithm, let's think of the log base 10. What you're doing, if you take log base 10, is you're saying what's important is not the exact value of a number, but whether the number is, whether it's a tens number, or a hundreds number, or a thousands number, or millions number. Logarithm seems exotic, but in fact, we think that way all the time. If you do well, you're going to make 100K a year. Then at some point, maybe you're going to make 1 million a year. There were 5 people on Wall Street who made $1 billion each year last year. Okay, so that's 3 orders of magnitude bigger. We think logarithmically, right? All right. So I have 5 minutes left. A small comment. Suppose the system changes, and I have an initial state with some entropy, and I have some final state. I'm often going to look at the changes. Delta S equals S final minus S initial is K log W final minus K log W initial is K log, because of the way logarithms work, ratio of final to initial. I'm not saying anything deep there, that's just the way logarithms work. Okay, so let's quickly then get the notion of temperature. Oh, wait a minute, so I have 5 minutes left. Was my watch, what time do you guys have? Huh? I think that's fast, but let's stop then, because this actually is, it's not going to take me long, but it's actually pretty deep, and I don't want to rush it. All right, so I'll see you next time.